Most forecasting demos stop at one step ahead. Real systems have to survive the whole horizon. This is the pattern you'll be able to implement by the end, which compares direct and recursive strategies and then forecasts multiple future steps with the chosen approach. I'm Professor Pi, teaching AI foundations with simple Python. Forecasting many steps ahead matters in real workflows. Planning inventory, scheduling crew, or allocating compute all need a sequence of future estimates, not a single next value. People reach for multi-step forecasting because single-step models mislead downstream systems that expect a full horizon. Scikit-learn is a good fit when your data is tabular, your horizons are short to medium, and you prefer simple, interpretable pipelines over heavy neural networks. At a high level, there are two patterns. Recursive forecasting trains one model to predict the next step, and then feeds that prediction back in to predict the following step. Direct forecasting trains a separate model for each final offset, so each model predicts its assigned future step directly. Recursive models reuse a single estimator and can be data efficient. Direct models avoid error compounding because they never use model predictions as inputs. We will build a tiny synthetic series to keep everything visible. First, we score a naive one-step baseline. Then we fit a linear model on lagged features for the immediate next step. After that, we show how to roll that model forward recursively for 3 steps. Then we train separate models to predict each of those 3 offsets directly. Finally, we tune regularization to steady the direct forecasts. Now, we create the tiny series and score a naive one-step baseline. This snippet creates a small synthetic time series and scores a one-step naive forecast. The variable t holds time indices, and y is generated as a gentle upward trend with a seasonal sine wave and small Gaussian noise. The arrays ypred and ytrue align consecutive points, so the naive strategy predicts the next value using the last observed value. The code then computes mean absolute error with NumPy, which captures average absolute deviation across the full horizon. A higher error here signals larger average step-to-step changes in the data. The printed naive may shows the baseline difficulty of predicting the immediate next step and sets a benchmark to beat. Next, we build lag features and fit a linear model to predict the immediate next step. This example trains a scikit-learn linear regression to beat the naive baseline using lagged inputs. The list lags defines which past steps to use, and max lag ensures features and targets align. The matrix X stacks the one-step and seasonal 12-step lags, while YT is the next step target. A simple split reserves the tail for testing, so we see generalization beyond the fit window. The model LR learns a linear mapping from lag features to the next value, and LR.predict makes out-of-sample predictions. Increasing the number of lags can capture more structure, but may overfit. Regularization can help later. The printed linreg one-step MAE indicates how much a basic linear model improves next step accuracy. Now we roll that one-step model forward to generate a 3-step forecast. This code rolls the scikit-learn linear regression forward recursively to make a 3-step forecast. The variable start marks the first test position, and hist holds the recent window required by the lag features. Inside the loop, X is built from the latest values in hist. LR_predict produces the next estimate, and that estimate is appended back into hist to simulate how future inputs depend on prior predictions. The array true slices the ground truth for those same 3 future steps. Finally, mean absolute error, REC-MAE, summarizes the multi-step deviation. Longer horizons increase error compounding, because each new step feeds on previous uncertainty. The printed recursive H3 may shows how quickly accuracy degrades across 3 steps. Next, we'll train separate models for each horizon step, so each predicts its target directly. This example switches to scikit-learn direct forecasting by training one ridge model per horizon step. The matrix X2 reuses the lag features but trims rows so every target column aligns. The matrix Y stacks the next 3 future values side by side, letting each model learn to predict a fixed offset directly. The list MS holds 3 independently fit ridge estimators via ridge with alpha equal to 1.0, and preds collects their aligned predictions for the first test row. Direct training avoids feeding model guesses back into inputs, which reduces error propagation across steps. Stronger regularization can stabilize coefficients when lags grow. The printed direct H3 may reflects the average error across all 3 forecasted steps. Finally, we'll tune regularization to stabilize the direct predictions. This snippet tightens the direct approach by increasing scikit-learn ridge regularization. The variable alpha2 controls weight shrinkage. A larger value reduces variance by pulling coefficients towards 0. The list MS2 refits one ridge per horizon using the same aligned X2 and Y as before. The array preds2 gathers the tuned predictions, and tuned MAE computes the new average 3-step error for the held-out case. The variable gain captures the improvement relative to the earlier direct result dir MAE. Raising alpha generally helps when features are correlated or data are noisy, but too much shrinkage can underfit and raise error. The printed, tuned direct MAE and gain quantify how regularization steadies multi-step accuracy. In a real project, you would apply this pattern across hundreds of similar time series. Create lagged datasets in a sliding window, fit models in parallel for each offset, and evaluate average horizon error across all series. This keeps the same core code, but scales to thousands of SKUs or sensor streams, while preserving the clarity of direct versus recursive choices. Recap: it is the comparison between recursive forecasts that reuse one-step models and direct forecasts that train one model per step. Use recursive when data is scarce and you want a compact pipeline, and use direct when you care about stable multi-step accuracy and can train separate models. One caveat: recursive methods compound prediction error across steps and can degrade quickly for longer horizons. Wrap punch. Next, tune the ridge alpha across a validation grid to find the sweet spot that reduces 3-step error without underfitting. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.